Good morning. My name is Alexander Chaban, and today, on behalf of my co-authors, I will be presenting our work titled Knowledge Integration Graph Networks for Interpretable Cardiac MRI Analysis. This presentation will cover the motivation for our work, our proposed two-stage framework, the experimental results, and the summary of our contributions and their implication for cardiology. Deep learning has shown immense promise for cardiac MRI analysis, but its clinical adoption is hindered by a significant trust deficit. The first major issue is that standard AI models frequently produce segmentation with anatomically impossible errors, such as disconnected heart walls. These errors can invalidate subsequent clinical measurements and ultimately erode a clinician's trust in the system. The second problem is the black box dilemma. Most deep learning models provide a diagnosis without offering insight into their decision-making process. This lack of transparency is fundamentally incompatible with medical practice, which demands clear evidence-based reasoning for every clinical decision. This brings us to our central hypothesis. By systematically infusing anatomical and clinical knowledge directly in the AI pipeline, we can create a system that is not only more accurate, but also fundamentally more robust, interpretable, and trustworthy for clinical use. Our work introduces a novel framework to address these problems. Our first core contribution is SCIF-SEG, a segmentation network that uses an expert-guided attention mechanism and a novel topologically aware loss to enforce anatomical correctness in its outputs. Our second contribution is KI-GCN, a graph convolutional network designed for interpretability. It models the heart as a structured graph, enabling transparent relation reasoning process for diagnosis that mirrors the expertise of a human clinician. Finally, we conduct a comprehensive validation of our framework on public benchmark. This rigorous evaluation on the ACDC and M&EMS2 datasets is designed to prove the superior accuracy, robustness, and interpretability of our integrated approach. This diagram provides a high-level overview of our two-stage pipeline. On the left, a raw cardiac MRI slice is fed into our segmentation network. This produces an anatomically constrained map, which is then used to construct a patient-specific graph that is finally passed to our classifier for interpretable diagnosis. The first stage, which we call synergetic segmentation, is handled by our SCIF-SEG network. Its primary role is to generate highly accurate and critically anatomically plausible delineation of the key cardiac structures. In the second stage, our graph-based diagnosis model, the KI-GCN, takes over. It performs cardiomyopathy diagnosis not from raw pixels, but from structured relational representation of the heart, which is key to achieving interpretability. Drilling down into stage 1, our SCIF-SEG network enhanced a standard UNet with two key innovations. An expert-guided attention model enables us to inject special priors, focusing the model on challenging regions. More importantly, our custom TAC loss function combines standard segmentation metrics with explicit penalties for anatomical violations, such illogical overlaps or disconnected structures. The key idea here is that by integrating these constraints directly into the training process, the network is forced to learn future representation that are inherently more consistent with anatomical reality rather than relying on the post-processing to fix errors. Now for stage 2, we will move from pixel to clinical concepts. The core idea of our KI-GCN classifiers is to abstract the segmented heart into a structured graph, which proves a natural framework for transparent reasoning. The graph construction is guided by domain knowledge. Nodes represent anatomical parts such as ventricles and myocardium, while edges encode predefines the physiological relationship. Each node is then enriched with a feature vector containing both clinical metrics and deep features learned by the segmentation network. A graph convolutional network then performs classification by passing messages between these nodes. After several rounds of information aggregation, a global pooling layer generates a final graph-level representation, which is then fed to a classifier to produce the final diagnosis. To validate our framework, we use two public datasets, ACDC as our primary benchmark and the more diverse M&Ms2 dataset to test generalization. All images were standardized through resampling and intensity normalization. We evaluate performance using a comprehensive set of metrics for segmentation quality, topological plausibility, and diagnostic accuracy. Turning to our results, the first table showed the overall segmentation performance on the ACDC dataset. Our SCIF-SEC models achieved a state-of-the-art DICE score of 91.2% and the lowest boundary error. As the charts illustrate, this is the significant improvement over both a baseline UNet and the standard attention UNet. When we break down the performance by anatomical structure, we see that our knowledge integrated approach provides consistent gains across the board. The most significant improvements, however, are for myocardium. This finding highlights that our method is particularly effective in addressing the most challenging aspect of the anatomy. Focusing on the myocardium highlights the clinical impacts. SCIF-SEC boosted the DICE score from 84.3% to over 87%. More importantly, as shown on the right, it reduces the boundary error by over 31% compared to the baseline. This superior boundary accuracy is crucial for deriving reliable measurements such as myocardial mass, which are essential for disease monitoring. A key goal of this work was to reduce anatomically impossible errors, and our TEC loss achieved significant success in this regard. As the data show, SCIF-SEC drastically reduces all forms of topological violation, including breaks in the myocardial ring. The overall topological errors rate was slashed by over 60%, confirming that our model produces far more anatomically sound segmentations. To understand the source of these performance gains, we conducted an ablation study. We found that adding our TEC loss provided the more substantial performance boost. Subsequently, adding the expert-guided attention model yielded a further synergetic improvement to confirm that both of the novel components contribute to the final state-of-the-art performance. To assess real-world utility, we performed a rigorous domain shift experiment. We trained our model only on ACDC data and tested it on the unseen M&Ms2 dataset without fine-tuning. The results showed only a minor decline in performance, demonstrating strong generalization. This suggests that by encoding anatomical knowledge, our model learns the fundamental features, making it robust to various variations across different scanners. And ultimately, the goal is to achieve an accurate diagnosis. Our KI-GCN classifier achieved a high macro F1 score of 0.87 and an excellent macro AUC of 0.986 for 5-class cardiomyopathy classification. The ROC curves on the left and the confusion matrix on the right both show strong balanced performance across all 5 disease categories, confirming the effectiveness of our graph-based approach. Beyond accuracy, a trustworthy AI must be reliable and consistent. The precision recall curves on the left show high average precision, indicating robust performance. Furthermore, the calibration plot on the right confirms the model predicted probabilities are reliable and a very low expected calibration error. This means a predicted 90% confidence truly reflects a 90% likelihood of being correct. Crucially, our KI-GCN provides interpretability that fosters trust. Using an explainer tool, we can see which parts of the heart the model focused on for its diagnosis. The analysis shows it consistently prioritized the myocardium and the left ventricle at end systole. This aligns perfectly with clinical practice, confirming that our model has learned clinically valid reasoning patterns. In conclusion, we introduced a knowledge-integrated framework that directly addresses the clinical barriers of anatomical implausibility and the black box problem in cardiac MRI analysis. Our SCIF-SEC network produces anatomically faithful segmentation, improving the myocardium DICE to 87.1%, and more importantly, reducing clinical boundary errors by over 30%. Our KI-GCN classifier then leverages this high-quality segmentation to achieve a high macro F1 score of 8 0.871, all while providing transparent and interpretable reasoning that aligns with established clinical expertise. Our key takeaway is this: explicitly encoded clinical and anatomical knowledge creates a more robust, accurate, and trustworthy AI system. We believe this work helps pave the way for more reliable and adoptable AI tools in the field of cardiology. Thank you for your attention. I would be happy to answer any question you may have.